Hello, everyone, and thank you for joining us today. Welcome to Megger's monthly Testing Tactics webinar series. Today's topic is understanding sweep frequency response analysis and best field practices. My name is Michael Fleischer, and I'm the digital marketing specialist for Megger. I'll be acting as the moderator for today's presentation and supporting you on any technical issues or questions for our presenter. On the right side of your screen, you will see a control panel. Sanket, it looks like we have a screen issue on there. We're only seeing a blue screen. There we go. All right, beautiful. So you'll see a control panel that will look similar to the one that Sanket's going to throw up there. You can submit questions at any time during the presentation by typing in the box highlighted in red, and I will read the questions out during the Q&A segment at the end of the webinar. All webinar attendees are eligible to receive 1 META CTD and 1 PDH or 0.1 CEU for attending. You will receive this in an email within 2 business days of the webinar. That email will also include a copy of the PowerPoint presentation and a link to a video recording of the webinar if you'd like to watch it again or share with your colleagues. Remember, you can ask questions at any time during the presentation, and they will be answered at the end of the webinar during the Q&A session. Also, please note that GoToWebinar has higher than usual traffic, and errors on their servers may occur. We will do everything we can on our side to mitigate these issues, but our options will be limited. Our presenter today is Sanket Bolar, Applications Engineer. Also, to assist with today's Q&A session is Jill Duplessis, Global Technical Marketing Manager, and Volney Naranjo, Applications Engineer. So let's go ahead and get started. Thank you for joining us today, Sanket.
Thanks, Mike. All right, let's get started with the presentation. Before we get started, let me thank you for attending the webinar. It is a tough time, so thanks for taking time out to attend this. All right, so we're going to be talking about sweep frequency response analysis in this presentation. And we're going to be going over the following points in the course of this webinar. We're going to talk about the objective of doing this test. Why is this test done? We're going to talk about the theory behind it. We're going to talk about the procedure. How is this test done? We're going to talk about the test data that we get out of it. What do we do with those test results? And eventually, we're going to talk about some best practice tips, some key measures that we can follow to get good and reliable test results. We're going to talk about what Megger has to offer in this field. All right, so let's get started. Let's begin by talking about why this test is done. So this test is called a fingerprint test. The objective of doing this test is to evaluate the geometrical and mechanical integrity of the transformer. Right? There are different tests that are done on transformers like turns ratio, winding resistance, power factor. Each of these tests serve a purpose. The winding resistance test is done to check the condition of the winding, to look for any broken strands, to look for shorted turns, to look for bad tap changer contacts, loose connections, things of that sort. A power factor test is done to look for any deterioration in the insulation. Just like these tests, SFRA has the objective of looking at the physical aspects. So it looks at the geometrical integrity of the transformer. Why is this test called a fingerprint test? It's because it's a site reference test. So when you do a turns ratio test, for example, you get a percentage error, right? You measure the turns ratio and compare it with the calculated turns ratio, and you get that percentage error. And if that percentage error is within plus minus 0.5%, then the test is considered, the transformer is considered to have passed the test. If it's outside the limits, then it's a fail. Unlike a turns ratio test, here we don't get a set of numbers which we compare against set limits. What we get is a test data which is unique to that transformer, and we use that test data for comparison. There are different ways of comparing results, and we're going to look into that later. But that's the reason why this test is called a fingerprint test or a signature test. It's because the test data that we get out of it is unique to the transformer that we are testing on. So let's talk about when is this test done. This test is done whenever a transformer is subjected to a condition where there are chances of physical changes occurring inside the transformer, where there is chance of transformer sustaining uh, a heavy impact resulting in considerable physical damage to the components inside the transformer. What are those conditions? Some of those conditions are provided on this slide. Transport. So the transporting a transformer from the manufacturer to the substation is a tedious process. It involves a lot of planning. It takes a lot of time and effort. If an incident occurs during this process, which is big enough to impact the transformer, cause any sort of physical damage to the transformer, then that those kinds of changes can be detected using an SFRA test. So an SFRA test is the last test typically done by the manufacturer before dispatch, and it's the first test. It's recommended that it be the first test to be done on the transformer as soon as it arrives on the substation. And then these SFRA test results before and after transport are compared with each other, and any sort of significant deviation indicates that there has been some sort of physical impact which the transformer has been subjected to while it was being transported. And then further investigation needs to be carried out to see the extent of the damage and to figure out what action needs to be taken. Another scenario in which SFRA could be used is after a dynamic withstand short circuit test. So dynamic withstand short circuit test is not to be confused with a short circuit impedance test, which is one of the factory acceptance tests done by the manufacturers. Dynamic withstand short circuit test is a special test. It's a design verification test, which is done on critical transformers. There are special facilities, few facilities in the world which have the capacity to do this testing on big transformers. So the transformer is taken to that facility, and then basically the transformer is subjected to short circuit conditions. There are breakers on the secondary winding, and these breakers are shorted, are closed when the transformer is energized at rated voltage, and that results in short circuit forces. Now these forces can be significant enough to deform the windings, to damage the windings. And one way of verifying whether the transformer has a good enough design, whether the transformer is able to withstand this test, is to do an SFRA. So SFRA test, the SFRA is done on the transformer before the test, and then after the test, and the test results are compared to look for any deviations. The SFRA test, although it's a special test, can be done as part of a maintenance program to do a general condition assessment evaluation on transformers which have been in service for a long time. Also, if a transformer is subjected to a fault, then one way to look for any physical damage to that transformer is by doing an SFRA test. So far we have talked about what the objective of doing this test is, and in what scenarios can this test be done. Now let's talk about what exactly this test is. Let's talk about the theory of it. So the transformer can be considered to be a complex RLC circuit, right? If you talk about it in very simple terms, you can say that the transformer has windings in it. The windings are basically coils which are mounted on a core. The core is made up of laminated sheets of high grade steel, and that forms the magnetic circuit. So the winding coils are mounted on the core, and then through electromagnetic induction, you have the transfer of electrical energy to magnetic energy, and then back to electrical energy. Right. So the windings operate at different voltages. They need to be isolated from each other. And how is that done? The windings have paper insulation on them. And then there are barriers between windings. There are wooden blocks for support. It's typically filled with mineral oil. Other liquids could also be used, but typically what you see is essentially paper and oil insulation inside the transformer to insulate the windings from each other and to insulate the windings from the ground, which is the tank. So all of these things that I mentioned, these in electrical terms, if we talk about them in strictly electrical terms, we can say that the windings are essentially conductors, right? Them being conductors, they have resistance, and because they're in the form of coils on high permeability steel, they have a high amount of inductance on them. They are all the dielectrics that are present inside the transformer. They have a capacitance. Not only the capacitance not only exists between the windings and between the winding and ground, it also exists between the turns of the windings. Right, so there is interturn capacitance as well, not just interwinding and winding to ground. So all of these elements together form a complex system. Now, when we run the SFRA test on the transformer, the objective is not to find out what those numerical values are. We don't intend to find out what the R, L, and C is that makes up the system. What we intend to do is get data out of it, which is a reflection of that model, right? So based on what R, L's, and C's are present in the model, we get a certain plot. Now, the plot depends on the values of the R, L's, and C's, but we're not really concerned with finding out what those R, L's, and C's are. So if any change occurs, for example, let's say the winding gets deformed. If the winding gets deformed, then the geometry, winding geometry changes. Now that's going to affect the impedance of the transformer. It's going to affect the capacitance because now the distance between windings may have changed, or the winding to ground may have changed. So any sort of change that occurs inside the transformer will cause a change in the RLs and Cs, and that change will be reflected in the curve or the plot that we get out of an SFRA test. So far I have told you that we get a plot out of the SFRA test, and that plot is reflective of the complex model, the black box that the transformer is. Now, how do we get this plot, and what exactly is this plot? So what we do in this test is we inject a variable frequency low voltage signal. The magnitude of the signal is 10 volts peak to peak, and this signal is injected into one terminal on the transformer. Right? The transformer has multiple bushings on it. Can have typically a three-phase transformer. A delta Y three-phase transformer would have 7 bushings on it, right? 3 on the high side, 4 on the low side. So on one of those bushings, we apply a signal, and we get a response signal out of another terminal on the transformer. So we make the connections on 2 bushings on the transformer. On one bushing, the signal is injected. On the other bushing, the signal is measured. The response signal is measured. So we have the input signal and we have the response signal, and we plot the ratio of the output to the input signal. It's essentially the transfer function of that model. And that transfer function is plotted at different frequencies. So it's a variable signal, it's a variable frequency signal. The magnitude remains constant at 10 volts peak to peak, but the frequency varies between 20 hertz to 2 megahertz. So it's a very wide frequency range there. And in this frequency range, multiple measurements are done at different frequencies. And the magnitude of the transfer function changes at different frequencies because the inductive reactance and the capacitive reactance are dependent on the frequency. So the transfer function changes, so the values change with frequency, and by joining all those points, by plotting them on a graph, we get a unique curve on the graph. And we get 2 graphs. One is the magnitude of the transfer function, which is given in decibels. So it's 20 times log to the base 10 VO by VI. VO is the output signal, VI is the input voltage. The reason why it is expressed in decibels is because the output magnitude can vary over a wide range. So to keep the to express a graph in a concise manner, to plot it in a concise manner, we express the magnitude in decibels instead of the actual magnitude. The phase angle indicates the nature of the signal that's coming out of the transformer. The phase angle is essentially the phase angle difference between the output and the input signal. So the phase angle of the output signal with respect to the input signal. The plot that we get, of course, follows a unique path because the RLs and Cs are unique to that particular transformer. The model is unique to that particular transformer. So that's how we get the signature plots. So it's the transfer function that's plotted in the form of a Bode plot. So this is what the connection looks like. As I said earlier, the signal is injected at one point, the response signal is taken out of the other point. So what you see here are two sets of leads, right? The signal that's being injected, here is being done by the lead marked yellow, and then you have the reference lead, which is the red lead. The reason why there are two leads at the point where the signal is injected is because we do not want to, we want to discount the effect of the lead that is injecting the voltage signal. So the voltage measurement, the signal measurement is done at the terminal and not at the instrument. So that's the reason we have two leads here at the point where the signal is being injected. And then we have the measurement lead at the other bushing, which is measuring the signal that's coming out of the transformer. We have the ground, so the instrument is grounded to the transformer, and we have these grounding braids which drop from the C clamps down along the bushing, and they are grounded at the nearest point, which is typically the bushing flange. Now, the reason why that is done is because we want to keep the grounding loop as short as possible. This is a very sensitive test. Especially the high frequencies, the grounding does influence the curve that you get. So to get repeatable measurements at higher frequencies, we make sure that the grounding loop is as short as possible. This is done by using grounding braids instead of wires. So grounding braids, typically with a width of 2 centimeters, are dropped down and grounded at the nearest point, which is typically the bushing flange. You may not see any effects when you're testing on low voltage windings, but when we test on high voltage windings with those high voltage bushings being really long, the grounding leads will be longer, and that can affect your measurements. We'll talk more about all of that in the future slides. Now let's just move on and look at the typical data curve that you get out of a measurement. So the plot that we are looking at here is a Bode plot of the transfer function, and this is from an open circuit measurement. We'll talk about the different types of measurements that can be done as part of this test. For now, let's just look at one plot. So here we are looking at the magnitude and the phase plot. The magnitude, if you look at it, it follows a downward path, and then it goes up. Now let's try to figure out what's the logic behind this behavior. So in an open circuit measurement, what we do is we inject the signal into one coil, and we get this response signal out of that same coil. So we are essentially testing a winding coil, one winding coil with all the other coils open circuit. What happens in this case is a coil has an inductance, right? And the inductive reactance is dependent on the frequency. It increases with frequency. The capacitive reactance, on the other hand, decreases with frequency. So both of them kind of are have opposite behaviors. So as we increase the frequency, the inductive reactance increases, the capacitive reactance decreases. And what happens is initially, because at lower frequencies, now before we talk about that, let's talk about what the x-axis and the y-axis is. The x-axis is the frequency. It's expressed in a logarithmic scale because of the frequency range being so vast. And on the y-axis, you have the magnitude on the first plot, and you have the phase angle on the second plot. Now, coming back to what we're talking about, the magnitude, the XLs and the XCs. So when we are in the low frequency range, the XL is less than the XC, so the signal is inductive in nature. Now, if you look at the phase angle, you will see that the phase angle of that signal is close to minus 90 degrees. And that's because minus 90 degrees means that the output signal lags behind the input signal. And that's what happens if the signal is inductive in nature. So up until a certain point, the signal is inductive in nature, but as the frequency changes, there comes a point when XL becomes equal to XC, and that's called that frequency at which this happens is called the resonance frequency. So XL is equal to XC, and when the frequencies increase beyond that, the nature of the signal flips. The signal now becomes capacitive in nature. So if you look at the phase angle, it changes over to plus 90 degrees. Now the output signal leads the input signal, and if you look at the magnitude of the signal, it increases with frequency, and that's because XC is now decreasing further, XL is now greater than XC, so the signal is capacitive in nature. So as the frequency increases, the magnitude of the response signal increases because the capacitive reactance decreases. And then as we go higher on the frequency, all of these interactions occur between the various elements, and that results in the complex path that the curve follows. And you get this signature plot. Now this test doesn't comprise of just one plot, like just these two plots that we get. We do multiple measurements on a three-phase transformer, and we get a set of test results. These are the different types of measurements that can be done on a transformer. In this table, I have shown you the terminals for a single phase transformer. So you have a single phase transformer which has two bushings on either side. On the high side, the bushings are H1, H2. On the low side, the bushings are X1, X2. If you have a single phase transformer like that, these are the connections that you would make on a single phase transformer for the different types of measurements. So let's talk about each of these measurement types. Let's talk about open circuit measurements. If you just look at the table, you'll see it talks about the connections that needs to be done. In an open circuit measurement, what you do is you just apply a signal across the high voltage winding coil. Now, the open circuit measurement would also be done on the low side. So you would inject the signal into X1 and measure it X2. So open circuit measurements are done on each winding coil that's there in the transformer with all the other windings open circuited. In a short circuit measurement, the measurement is done across each high voltage winding coil. So this being a single phase transformer, we just inject the signal into H1, get the output signal like from H2, and the secondary winding is short circuited. So X1 and X2 are shorted. So we have discussed open circuit and short circuit measurements so far. The other two types of measurements that are there are called interwinding measurements, and the reason being that the signal is injected into one winding and you get the response signal from another winding. So the signal in this case is injected into H1 and you get the signal, a response signal from X1. There are two types of interwinding measurements. The difference between the two is in capacitive measurements, the other ends of the windings are not grounded. In inductive measurements, the other ends of the windings are grounded. Let's talk about each measurement a little bit more in detail, and let's look at typical measurement plots that you get. So in an open circuit measurement, as I said earlier, each winding coil is tested with all the other windings open circuited. So it's kind of comparable to an excitation current test. Now, an excitation current test is one of the field tests done on a transformer, where what you do is you energize the high voltage winding at a high voltage, typically 10 kV when you're testing really big transformers. And you measure the excitation current that the transformer winding draws. The excitation current that the transformer winding draws depends on the condition of the core and the winding, because the current essentially depends on the reluctance that the flux sees when it flows in the core. So if the core is corroded, if there's any defects in the core, then it will see a higher amount of reluctance. It'll draw more current. So things of that sort are related to excitation current. So any problems with the core, or if the winding has short-circuited returns, that will cause a problem as well. So any problems with the core or the winding could be detected using an excitation current test. And these are the effects that also show up in open circuit measurements. So if you have a problem with the core, if there's a problem with the core of the transformer that you're testing, then you will see deviations in your open circuit measurements, especially in the lower frequency range, because the lower frequency range is the area where the core has an influence. Short circuit measurement. In the case of a short circuit measurement, the high voltage winding coil is tested and the low voltage winding is short circuited. So if you're testing on a three-phase transformer, you would inject the signal across each high voltage winding coil. So A phase, B phase, and C phase. The low voltage winding, on the other hand, would be short circuited terminal to terminal. This test is comparable to a leakage reactance test. If you are familiar with the short circuit impedance test, which we kind of mentioned a little while back, what happens in a short circuit impedance test is at the factory, three-phase supply, a three-phase voltage is applied across the high voltage winding with the low voltage winding short circuited, and rated current is circulated. The amount of voltage needed to circulate rated current across a transformer is expressed as a percentage of the rated voltage, and that value is called the leakage impedance. The percentage leakage impedance or leakage reactance of the transformer is essentially the impedance that the transformer has because of the leakage flux inside the transformer. And leakage flux is the flux which doesn't link the primary and the secondary, right? So that value is again a characteristic of the transformer, and after this test, the value that's measured is punched on the nameplate of the transformer. So that's the short circuit impedance test. Now, one of the field tests that's done on a transformer is a leakage reactance test, where single phase measurements are done out in the field because you don't have the luxury of having a three-phase source with enough power to circulate rated current through the transformer when it's offline. So what you do is you inject a very small current through each phase with the secondary winding short circuited. So you get three measurements, three individual values, one for each phase. And from those three values, you calculate the equivalent three-phase impedance. Now that equivalent three-phase impedance is supposed to be very close to the percentage short circuit impedance given on the nameplate of the transformer. The IEEE field testing guide mentions a limit of 3%, so it should be within plus minus 3%. Now, the plot that you see here is a typical short circuit measurement plot. The magnitude of the plot is typically higher than what you see on your open circuit measurement, and that's because in an open circuit measurement, the magnetizing impedance of the transformer is in the picture, and that magnetizing impedance is much higher as compared to the short circuit impedance of the transformer, the leakage impedance. So that's the reason why short circuit measurements typically have a higher magnitude. A short circuit measurement plot won't be influenced by the core, so any problems in the core may not result in deviations in your short circuit measurements. So this again is the same plot. This plot, like the earlier plots, is the magnitude of the transfer function expressed in decibels, right? So we are looking at the ratio of the output signal to the input signal. Now, instead of looking at the magnitude of the transfer function, we can also express the same data points in terms of impedance. We do know what the measurement impedance is. The typical standard is 50 ohms. So from the transfer function, we can determine what the impedance of the system looks like, the system that we are testing, which is basically the transfer, right? And that impedance that we measure, that we determine, can be plotted from the short circuit measurement curve. So here we are looking at the impedance values of those measurements that we obtain at different frequencies. And this is what the curves look like for all three phases. So we have three curves here. You can see that those three curves line up perfectly up to a certain frequency, which here in this case is 4 kilohertz. And which is what's typically the case in higher frequencies. You see some differences between the three phases. So here we are looking at the impedance values, and this test was done on a 30 MVA, 138 by 25 kV DY-N1 transformer. So the high voltage winding is a delta connected winding. Now let's determine what the 60 Hertz impedance values are. At 60 Hertz, the impedance values from the graph are determined to be 127, 128, 127 ohms. Now from these three values, we can calculate what the three-phase equivalent impedance would be. This is the formula that's used if the high voltage winding is a delta connected winding. Using this formula, we get the value of 10.04%. Now the nameplate value that was given on the transformer was 9.74%. So the two values, as you can see, are pretty close to each other. So this is how you can kind of correlate your short circuit measurements with your percentage leakage reactance or your percentage impedance given on the transformer. Okay, so this is the kind of additional information that you can get out of your measurements, out of your SFRA measurements. Now let's talk about interwinding measurements. Let's start off with inductive interwinding measurements. So in the case of an inductive interwinding measurements, as I said earlier, what's done is the signal is injected into the high voltage winding, and the response signal is measured on the low voltage winding, on the corresponding phase on the low voltage winding. The other ends of the winding coils are grounded. And now this measurement is comparable to a turns ratio measurement, because essentially what you're doing is you're looking at the transformation relationship between the high voltage winding and the low voltage winding. The curve that you get typically looks like this. You have a horizontal, more or less horizontal line in the lower frequencies, and that line basically gives you, it corresponds to the transformation ratio between the two coils. Now this is the same plot blown up. Again, in this case, we are looking at the magnitude in terms of decibels, right? And we are looking at the transfer function, which is the ratio of the output to the input signal. The output signal is the voltage that appears across the low voltage winding. The input signal is the voltage that appears across the high voltage winding. So we are essentially looking at the ratio between the low voltage winding and the high voltage winding. And if we plot the same curve in terms of its true magnitude, instead of looking at decibels, we get a value of 0.036 at 60 Hertz for this particular transformer. Right? So in this plot, we are looking at the actual ratio of low voltage to high voltage. And we get a value of 0.036, and it's 0.036 for the most part in the lower frequency range. It starts to deviate in the higher frequencies. Right? So 0.036 is what we got on this transformer, but it's the ratio of low voltage to high voltage. And when we do a turns ratio test, what we do is we measure the ratio of high voltage to low voltage winding. Now, if we want to measure the turns ratio of this particular transformer, what we need to do is we need to find out the reciprocal of the value that we measured at 60 Hertz. So in this case, the measured turns ratio would be 27.695. The calculated turns ratio based on the rated nameplate voltages on this transformer is 27.496. 7620 by 480 volts is the voltage rating of the transformer. It's a DYN1 transformer. Because the low voltage winding is a Y connected winding, there is a factor of square root of 3 which appears in the formula. So you have 7620 divided by 480 by the square root of 3, and the value that you get is 27.496, and that's pretty close to what we measured using the SFRA test. So this is another way in which an SFRA measurement can be correlated to another test result, another test altogether. The fourth type of measurement is capacitive interwinding measurement. Now, in this case, the voltage is applied on the high voltage winding coil, and the response is measured on the corresponding low voltage winding coil. In this case, the other ends of the coils are not grounded. It's analogous to an interwinding capacitance measurement. So one of the other tests that's done on the transformer is a power factor test. And in a power factor test, what you do is you test the capacitances between windings and between the winding and the ground. And you get power factor values which are indicative of the quality of the insulation, but you also get capacitance values which tell you about the geometry of the windings, right? So you do look into the physical aspect when you do a power factor test as well. Now, when we run this test, because the coils are not grounded, it's analogous to doing that measurement, because we are looking at the insulation now between the windings. And what we get is a curve which is capacitive in nature. If you look at the magnitude of this plot, it increases with frequency, and that's because the signal is more or less capacitive in nature. So let's again do the same thing as what we did in a short circuit measurement. Let's look at the actual impedance of the system that we are looking at. When we plot it, the impedance value, of course, decreases with increase in frequency because it's essentially capacitive. And to find out what the 60 Hertz value is, we look at the value on the curve that corresponds to 60 Hertz, and we get a value of 3.537 mega ohms at 60.3963 Hertz. Now, from this value, we can determine what the capacitance is, because through this formula, the capacitance value that we calculate is 745 picofarads. Now, when a power factor test was done on this transformer, the measured interwinding capacitance was 738.7 picofarads. That's pretty close to the value that we determined from the SFRA measurement. Now, so far we have discussed the different types of measurements that are done as part of this test. Now let's talk about the different types of comparisons which can be done in this test. The first type of comparison which can be done is a time-based comparison, where we look at the previous test results done on the transformer. So if you have factory test reports from the transformer and you just did this test on the transformer on site, then you can run a time-based comparison between the two. You can run a comparison between the two test results, and you can look for deviations. If anything happened between the 2 points in time that the tests were done, then that would show up as a deviation in some of those measurements. The other way of doing this test, the other way of doing a comparison is a design-based comparison, where we compare the test results that we get on that particular transformer with a sister transformer. A sister transformer is a transformer which was manufactured as part of the same work order. So it was manufactured by the same manufacturer, has the same design, same materials were used. So it should have very similar responses, and the test results from a sister transformer can certainly be used for comparison. And then the third type of comparison is a phase-based comparison, where we compare the measurements done on the three phases. Now, this is the comparison that you would do if you do not have the previous two options. So you do not have any sister transformers, nor do you have any previous test results. In that case, what you can do is you can compare the three phases, and you will see differences between the three phases, but they'll follow each other for the most part. If there's something seriously wrong with one of those coils, then you will see a deviation on one of those coils. Now let's look at some examples of comparisons. Here we are looking at a time-based comparison done on a transformer. The two measurements were taken a year apart. You can see that there isn't much difference. There is some difference in the lower frequencies, and that can be because of the state of the core, can be because of the test setups. So minor deviations can show up even if there's nothing wrong with the transformer. This is a design-based comparison where we are looking at two different units of the same work order. So two generator step-up transformers, and you can see that they follow each other for the most part in the mid-frequency range, but in the higher frequencies there is some difference, and in the lower frequencies there is some shift, but it's pretty close for the most part. Here is an example. Here's another example for design-based comparison where we are looking at two different units. You can again see that there is some deviation in the lower frequency range up to about 10 kilohertz, 20 kilohertz. But after that, the two curves match up perfectly. This is an example of a phase-based comparison. These are three open circuit measurements done on each phase of a transformer. You can see that A and C would typically be closer to each other as compared to the middle phase, especially in the lower frequencies, and that's because, as I said earlier, in open circuit measurements, the core plays a part. The core return paths are different for the middle leg as compared to the extreme legs, which is the A and C phase. So A and C phase are kind of symmetrically opposite to each other, so they have pretty similar responses, whereas the B phase sees a different response because of it being located in the middle. This is another example of open circuit measurements done on the three phases. You can see it's a delta connected winding, and you can see on the middle phase the response is different in the lower frequency range. Now, these are some of the problems that are detected by the SFRA test. It includes radial hoop buckling, deformation of winding, axial winding elongation. So what happens is when the windings are subjected to short circuit conditions, and the high currents that are generated in these conditions give rise to physical forces. These forces are radial in nature as well as axial in nature. The radial forces are repulsive, which means that they push the outer windings outwards. They push the inner windings inwards towards the core. Axial, on the other hand, if there is even a minor imbalance in the ampere turns, that can result in significant axial movement of the windings. Besides that, there can be problems with the core, core grounding, core being corroded, things of that nature. Magnetism in the core can influence the readings. winding conditions, any interturn shorts, loosening of clamping. The windings are clamped under high pressure. The sheets are clamped together. So any problems with that can result in deviations, loose connections. Open circuit winding, of course, will cause deviations as well. So these are just some of the problems that can be highlighted by the SFRA. And different problems correspond to different frequency ranges. So no test is conclusive, can be conclusive by itself. So you do need to perform a bunch of tests to figure out exactly what's going on in the transformer. SFRA is no exception. It points towards a particular problem area, and then further tests may need to be done to determine what exactly may be causing those deviations. But these are the general problem areas which correspond to the different frequencies. And what you have is, in the lower frequencies, the core plays a part. In the middle frequencies, the windings, the interaction between the windings, the winding structure, and in the higher frequencies, the grounding has an influence. So this diagram was taken from the IEEE FRA testing guide, which is a good reference document, IEEE C57.149. If you need information on this particular testing, IEEE has a dedicated testing guide, and you can certainly refer to that. So coming to the last part of the presentation, we're going to talk about some best practice tips, some tips that you can follow to make sure that you get good, reliable test results, right? This test is a site reference test. It's all about comparison. So you want to make sure that you get repeatable, accurate test results, which can be used for future comparison. Also, you want to make sure that you make note of the conditions in which the tests were done, so that the guy who does this test, maybe 5 years, 10 years later, tries to replicate those conditions to get a fair comparison. So let's look at some of those points. The tap changer position, noting the tap changer position is important because the tap position does affect the readings. Tap changers are provided on transformers to change the number of turns of the winding, right? So if your transformer is tested at a different tap, it has a different number of turns now, and that changes everything. That will result in a different transformer. The IEEE testing guide recommends that for a winding which has an LTC, the test be done at extreme raise tap, where the whole winding is in the picture. If you are testing on a winding which has a DTC, then it just needs to be done on the in-service tab, because we don't want to fidget around with the DTC if it has been in a particular position for X number of years. Here's a plot to highlight the different responses that you get when you try to test the winding in different tabs. Also, something that's not shown here is if you are testing a winding which has an LTC and which has a reversing type LTC, and it is at the neutral tap position, you want to make sure that you change the tap in a certain order if you're testing at multiple taps, or at least mention the way the tap was changed to the neutral position. The reason being that if you change the tap from the low positions to neutral, then the reversing switch has a certain position which is different to the position that it would be in if the tap were changed from the raised positions to the neutral tap. So you may test on the neutral tap having changed the tap from 16R to neutral. You may also do that same test at the neutral tap position having changed the tap from 16L to neutral. In either case, you'll get a response which is different from the other. So you want to make sure that you make a mention on how the tap change was done and the tap was brought to the neutral position. Or if you are not going to do that, at least if you're going to measure at the extreme taps and then at the nominal tap, make sure that the tap is changed in a consistent manner. Note the condition of the transformer. Is the transformer oil filled or not? Having the transformer filled with oil or it being filled with air will result in different responses because oil and air have different dielectric properties, which basically means they have a different capacitance. So you will get different responses depending on what's there inside the what fluid is there inside the transformer. Bushings. So the manufacturer may have tested the transformer while the bushings were connected. When the transformer arrives on site, the bushings may have been disassembled. It's typically transported without the bushings. The big transformers are, at least. So even before the bushings are mounted, if you try to run an SFRA test, even if the transformer is oil filled, with or if even if it has a different set of terminations, you try to run the test, then you will get a response which is different from that which would be there on the factory test reports. So make sure that you know what terminations were used. If special terminations were used, then you need to use the same. If bushings were used, then you need to test with the bushings on the transformer. Core grounding does play a part. One of the tests that's done when the transformer arrives on site is checking the core grounding. So what's done is the core terminal is brought out on the transformer tank and it's grounded externally to make sure that the core can be tested for multiple grounding points, which is not a good thing. You don't want to have multiple grounding points on the core because that will result in circulating currents, resulting in arcing, gassing. So that's the reason one of the tests that's done on the core grounding is the core ground terminal is ungrounded, and you do an insulation resistance test there to look for any other grounding points that may be there inside the transformer. If you do that test and you don't ground the transformer back, you don't ground the core back before proceeding to the SFRA test, and then you run the SFRA test, then your measurements can be different because of the core now being not grounded. This is an example to show you what kind of differences may result. You have two plots. In one case, the core was grounded. In the other case, the core ground was removed. Keep the grounding loop short. As I said earlier, the length of the grounding braids that are dropped from the bushings down to the bushing flange can affect the measurement, especially in case of, especially when you test high voltage bushings, which are longer, and that's because the inductance of the leads interacts with the response of the transformer and influences it. So you can certainly see deviations in the higher frequency range when you use different lengths. So you want to make sure that to stay consistent, you make sure that the grounding braids are as short as possible, that the grounding braids are grounded at the nearest point, which is typically the bushing flange. So here you have two measurements done with different lengths of grounding braids in the circuit, and you can see that there are deviations in the higher frequency range. When you run short circuit measurements, you want to make sure that the secondary bushings are short circuited from point to point. If you use really long cables, then that creates additional resonance points. In the higher frequency range, as you can see in this example, so you can see that in the higher frequency range, the shorting does influence the measurements, the short circuit measurements. And then you have the magnetism in the core. So I spoke about how magnetism in the core can influence, and the deviations resulting from magnetism in the core is typically observed in open circuit measurements where the core has an influence in the low frequency range. One way of inducing magnetism in the core is by doing a winding resistance test. In a winding resistance test, what happens is a DC current is injected into the winding, and that DC winding sets up a unidirectional flux which magnetizes the core. The coil loses its inductive properties, and what we are left with is the resistance of the conductor, which is then measured by the test set. And that's the reason why we inject DC current. Now, because we do that, we magnetize the core, and if the core is not restored back to its original state, if it's not demagnetized, and then SFRA test is done, that can result in deviations in open circuit measurements. So this is an example to highlight the kind of difference that you can see. The red curve corresponds to the measurement done before doing a resistance test, and the blue one corresponds to curve. The blue one is the curve that we got after doing a winding resistance test. So you can see that there is a shift there in the lower frequency range. Some resistance test sets have demagnetization features in them. The demagnetization is done on site by injecting a sequence of alternating DC current pulses with decreasing magnitude, and that restores the core back to its original state. Now here you can see what happens after demagnetization. So measurement was done after demagnetization, and you can see that the curve pretty much matches up with what we got before we did the winding resistance test. The deviation that you see there is pretty minor, and that's kind of allowable. So moral of the story: make sure that you find out if your winding resistance test set has a reliable demagnetization feature in it. If it does, then it doesn't matter when you do the winding resistance test. But if your winding resistance test set doesn't have a demag feature in it, and you're planning to run an SFRA test, make sure that you run the SFRA test first, and then you run the winding resistance test. Another test which is influenced by magnetism in the core is excitation current. As I mentioned earlier, the open circuit measurements are analogous to excitation current. Both of these measurements are affected by magnetism in the core. This is a test which is very sensitive. The magnitude of the input signal is low. The magnitude of the response signal is even lower. This test is done over a wide frequency range. You want to make sure that interference from proximity to high voltage equipment doesn't exist. One way of looking for any disturbances is by doing a single point test, where what you do is you connect both leads on the high voltage bushing that you're testing on. Just one high voltage bushing. So both leads are connected on the same high voltage bushing, and you run a measurement. The response should pretty much be at 0 decibels, but at higher frequencies, you'll see that it starts to deviate, and that's the point at which I guess the noise plays a role in influencing the measurement. Isolate the transformer, make sure that the transformer isn't connected to anything else in the system. If it does, then you will get the response of not just the transformer, but also the system that's connected to it. If it's connected to a bus bar, for example, even if the bus bar is not connected to anything else, make sure that you mention the report that if you tested it with the bus bar, that needs to be, then the next guy who runs the same test needs to know about it, because that can also influence the measurement. Note the test voltage. The test voltage magnitude needs to be noted, because that can influence the response that you get. Here is an example to show you. In this case, there are 3 curves that you can see. Each of these measurements were done at different voltages, 1 volt, 5 volts, and 10 volts. You can see that it caused a difference in the lower frequencies. So these were the best practice tips with regards to SFRA. Now let's talk about what we have to offer in the field of FRA testing. The instrument that we offer is called the Frags. There are different models available. We provide one with an onboard display. We also provide one which is a really small piece of equipment which can be used, which can be operated through your laptop via Bluetooth. As far as specs are concerned, the frequency range goes all the way up to 25 megahertz. So it's well covers the frequency range. That's the industry norm, which is 20 hertz to 2 megahertz. The measurement time is 37 seconds. That's for each measurement run from 20 hertz to 2 megahertz. The sampling rate is 100 million samples per second. The compliance voltage goes all the way up to 24 volts peak to peak, again, well above the typical test magnitude of 10 volts peak to peak. The number of sampling points by default is 1046, can go all the way up to 32,000 points if you want more information, and it's user selectable. You want to make sure that the test set that you use has a good signal to noise ratio at low magnitudes. The magnitudes on open circuit measurements on some transformers can drop to as low as minus 90 decibels. You want to make sure that the instrument is capable of giving you reliable measurements at those decibel levels. We provide a field test box, which is one way to check the instrument response before you start the test, just to make sure that your instrument is in good working condition. So we provide that as an accessory, and that's a very good practice too, to have this accessory. And the response of this accessory goes all the way down to minus 100 decibels. And you get a clean response out of our instrument, and that kind of highlights the effectiveness of our measurement of our instrument at low decibels. The software, this test is all about comparison. So when you get test data from two different manufacturers, you want to be able to compare those test results. Our software is compatible with a lot of other file formats, so it can be used for comparison. Faster measurement time can be achieved by changing the sampling points, the number of sampling points. So that's user selectable. In the lower frequencies, typically there aren't as many resonance points, and the response is much smoother, and it doesn't require a high level of sampling. So the number of sampling points can be used in the low, can be reduced in the lower frequencies. That's how you can get faster measurement times. The contact needs to be proper. You need to have a solid connection, and that's the reason why we provide C clamps like this. And we also provide a field demo box, which can be used as a training tool to highlight the way the SFRA test functions. So there are different conditions which can be simulated on the demo box, and you can see the different SFRA responses that you get when these different conditions are simulated on the box. My name is Sanket Bolar. Thank you for attending the presentation. Please help us improve by filling out the survey, which appears at the end of the webinar. Mike?
All right. Yeah, thanks. So at this point in time, the presentation portion of the webinar has officially concluded. We'll take about 30 minutes to answer as many of your questions as possible. If you have questions, please submit them now in the Q&A box on the right side of your screen. For those of you that are leaving, when you close the webinar window, a survey should pop up on the screen. We would greatly appreciate it if you took a few minutes to let us know, to provide your feedback so we can continue to improve upon future webinars. On the survey, there's a field where you can also request a demo or a quote on any Megger products. A copy of the presentation, along with a link to the video recording of this webinar, will be emailed to everyone in about a week, hopefully 2 business days. You can also view video recordings of previous webinars on our website at us.megger.com/webinars and register for next month's webinar, medium voltage and high voltage cable fault location utilizing our method. The presenter will be Javier Ruiz. So let's get into your questions. The first one we have is for Jill. Jill, you with us?
Yes, I'm right here, Mike.
Perfect. All right, here you go. What is your peak-to-peak value of the VI voltage? Sorry.
Yep, input voltage. Sure. So I know at the end of the presentation, and I do realize that some of these questions probably came in before all of the slides were complete, but I know that Sanket mentioned that the range for voltage of Megger's Frags, that's our SFRA test instrument, went up to 24 volts peak to peak. The default for the instrument is the really traditional widespread one that's adopted. It's 10 volt peak to peak test voltage. So it will default to that, but certainly the user has the ability to change that test voltage if needed, particularly if you're trying to import some other SFRA traces that perhaps were performed at different voltages. Of course, you want to make sure if you have the value of being able to compare to previous, which is gold for analysis of SFRA test results, you should certainly decide, hey, you know what, instead of testing at 10 volts peak to peak, I want to match this previous, and you have the ability to change your test voltage to any other one that may match a previous test result. And why I have the little podium, so to speak here, virtual podium. Let me just mention one other thing about the Frags, which is pretty cool. I know that Sanket had talked about grounding and the importance of grounding in an SFRA test and analyzing the results, particularly in a very high frequency range. One thing that the Megger Frags has as well is a ground loop detecting circuit. So basically, it's going to give you a green light if it detects that your grounding circuit is good, and it will alert you to those circumstances where maybe you don't have the ground tethered to the bottom of the bushing flange of a connection. Maybe it's been painted and that is a really good connecting point, and you don't know it, but you don't have a very good ground. It does. The Frags does have a detection loop to alert you of those situations when your grounding isn't good. So sorry to add that extra bit in there, but I just wanted to, before I forgot, to mention that as well.
Yeah, of course. So moving along, our next question is going to be from Volney. So will these tests also work for dry type transformers or only oil field transformers?
So it's a test in which you apply a signal and you measure the response. So any apparatus that you have some inductive and capacitive effect there, you will have a response. And yes, of course, it will apply for dry type transformers. However, one little thing I want to mention is that the IEEE standard C57149, it shows in the title that it's only for oil field transformers. But other than that, I guess that it's a little precaution there to show that most of the information shown there is about oil field transformers, but it definitely applies for other type of transformers.
Perfect. Over to Jill. What is the smallest transformer size this type of testing is done on? I'm an industrial user and have transformers that are typically 5 MVA and smaller.
Okay, so that's an interesting question. I wouldn't say so much that there's necessarily a limit on what size transformer you would do. I would mention, however, with regard to winding voltage, when you get to the lower voltage windings, and you saw this in Sanket's presentation, the transfer function, the dB plot of the magnitude of that transfer function for a low voltage open circuit test is generally, scrunched. Sorry for the non-technical word. It's really pushed to near 0 dB. It's a lot. It doesn't have anywhere near the impedance of a higher voltage trace. So if I was testing, if my population of transformers are, ones, and again I would look at the voltage of the windings more than the size of the transformer. I would, with the Megger Frags, in addition to looking at the transfer function, which is what you most of the time or first thing you're looking at is that plot, that dB magnitude plot. I would also, the Frags also provides the opportunity to look at the admittance, and essentially in Sanket I'd explained what we're looking at when we do a measurement on an FRA measurement on a transformer. But then what we get with the transfer function, it's not isolating per se that admittance or impedance value. And so, however, the software for the Frags will provide a view of that admittance information, and particularly for low voltage windings. This can be really helpful to look at that instead, because it gives you a lot more detail when you're analyzing these traces. We're really interested in, gosh, what are the resonances on this trace and what frequency are these happening at? And if I have previous test results, are there additional resonance points or suddenly from the last time I tested? Because that would be unusual. Or did I lose a resonance point and everything? If your response is too close to that 0 dB axis on the magnitude plot, you can lose some of that information in those resonance areas. And so in the ability, it could get flattened, it looks a little flat maybe. You can get a lot more of those details back if you just jump over. It's literally pushing a tab to jump over to an admittance plot, because that then separates the true admittance of the transformer. So it kind of really gives the appearance of the magnitude plot, plotted in dB, but it's the true admittance of the transformer. It looks similar. It just kind of gets shifted over to the right a bit, but it pulls everything. It has the influence where it tends to pull everything down on the plot, and so it sharpens up resonance points on those low voltage windings. So that would be my recommendation if you're testing. I would look more at what kind of winding voltages am I dealing with? Because in those cases, then I think you would really appreciate the value of looking at admittance, or conversely, it's just kind of like it does the mirror image of it really, but at the impedance plot, those would both be much more sharp results to look at in those cases, and give you the ability to catch more changes from previous in the event you had some kind of a mechanical problem with the transformer.
Perfect. All right. Next question. We're just trying to run through as many of these questions as we can. Volney, how much deviation is accepted when comparing traces? How much variation on the SFRA curve is significant? How many decibels, and at which frequencies?
So all of these are different questions we got from different people, but it's all relates to the same. It's about the analysis of the result. When you see the differences, the indication is that if there's any difference, there's a problem. So then you ask the next question, which is how much difference, or how big of a difference is important. So it's not an easy question to answer. The standards that we have available, the IEEE standard and also a Chinese standard, DLT 911, those standards have a statistical analysis method in which they compare both curves, and depending on the statistical analysis, they will generate some coefficients, and those coefficients are compared to some minimum values or some limits. So you could have only one difference at a very specific frequency, but a very high decibel variation, higher than 5 or 3 decibels, but it's only one and might not be significant. Or you could have very small variations throughout the entire frequency range. So the best way is to go with those statistical methods, and the software of the instrument has those implemented, so you can see right away when you compare two traces if the differences are indication of a severe deformation or a normal condition. Just to give some basic examples, I've seen cases in where there's small variations, small differences or few differences in a couple of frequencies, but with variations of 3 decibels. And after visual inspection, they have seen some damages there, some changes inside the transformer. But again, it's just one case. There could be many situations. So the best thing is always to go with the statistical analysis from the standards.
Cool. So Jill, does a magnetized core affect the tests?
Okay, I'm actually really glad for this question. It probably came in before Sanket had shown that, in fact, it of course does. And he showed the graph, after, I think it was after winding resistance tests had been performed, and then after maybe before and after, or after it had been demagnetized, and showed in the lower frequency range where the core impedance is dominating the measurement, that it shows a shift whenever a core gets magnetized. It kind of shows this predictable shift up to the right of the magnitude response. So I'm glad this was asked, because it's completely conceivable and possible that you do a SFRA test, and then maybe you've got the advantage of having previous test results, and you're like, gosh, they're not overlaying, and I didn't just do it. I didn't do a DC winding resistance measurement. I haven't done that yet. There's such a thing that's called magnetic viscosity. Basically, it's a situation where the magnetization level of the transformer's core is varying with time. And when I'm talking with time, I'm talking over days or weeks. It's a phenomena that happens, and it's kind of anytime a transformer is de-energized, for example, or energized, it can cause a slowly varying magnetic change to take place in a transformer. So in an ideal world, to be honest with you, I mean, if you had a winding resistance instrument that had the ability, and you had confidence in its ability to fully demagnetize the transformer core, then, I mean, it would be nice to, before you do your SFRA test, to demagnetize it with that instrument and get it into this precise neutral state. And then next time you do your SFRA test, again, demagnetize the core, because if you and then do the test, because that way hey, I've got this in this precise neutral state. But even if I did a test, I took the transformer out of service today and I did an SFRA measurement, if I came back and next week and I performed SFRA testing on this transformer and it's been sitting there de-energized, it's conceivable that in those low frequency ranges that there could be a shift, because the magnetic state of that core is different over that week of lapse in between those tests. And that's no reason to be alarmed. You're just seeing with the test results that it in fact is very dependent on the level of core magnetization, and to recognize what that looks like, and when possible, if to demagnetize the transformer and see if that resolves the issue, and the results are comparing better.
All right, excellent. Sanket, the question for you is, can the Frags perform DFR functions if the windings are shorted and not grounded, as in the standard power factor / winding capacitance tests?
Okay, so I have had a question similar to this before from other people, where they've asked me, people do tend to get confused a little bit between SFRA and DFR, because both tests are done at multiple frequencies. But that's where the similarity ends. They are variable frequency tests, but they do entirely different things. What the DFR does is it does power factor testing at different frequencies, and you get a plot. But it does power factor testing, which involves loss measurement, right? What the Frags does at multiple frequencies is inject a voltage and then get a signal and then measures the ratio of the output to the input. So it doesn't do any loss measurements. And that's why the Frags cannot be used for doing what the DFR does. So these are two different tests. The only common point between them is that they are done at multiple frequencies and you get a plot. But yeah, that's the only thing that's kind of similar between the two tests. Everything else is different. I did mention how you can get the capacitance value from the interwinding capacitance measurement, capacitive measurement, but that's all you can get. You can get the capacitance value because you get the impedance value of the system. You cannot get a power factor value from a Frags because the Frags doesn't do loss measurement.
All right. Next question is going to be for Jill. How close is pretty close? Like, is plus or minus 5% okay, or is plus or minus 10%? At what point would the difference be cause for concern?
Okay, these are great questions, and I mean, like cut to the chase. This is probably, I mean, I think we're seeing so many similar questions because, of course, the analysis of it is, you know, it probably feels a little uncomfortable that, gosh, you know, I don't have steadfast limits, so what am I to do with this? But I will say the answer, I mean, one thing I would point out, and and maybe add on to how Volney answered a similar question a few back, it depends. I mean, in some tests that you're going to do with the SFRA, the short circuit SFRA test measurement, those are very, like Sanket has said in his presentation, those are very similar to performing a leakage reactance test. And so if you zoom in on the short circuit measurements on the linear part of that inductive roll-off of that test, I mean, there are, and for some SFRA tests, there are definitive boundaries. Like for that, you expect all three phase measurements of those short-circuited tests to be practically the same. So if you use the zoom feature and you really magnify that area, those traces should be within 0.1 dB of each other. They should be really, really close. Otherwise, that could be an indication that, you know, you have some winding deformation. The interwinding SFRA measurement, the capacitive, I should be specific because there's a capacitive interwinding and an inductive interwinding. The capacitive interwinding SFRA test is one that is essentially provides the capacitance information that you would get had you done a power factor dissipation factor test. So that can always be used, of course, as a backup if you suspected winding deformation. Say I zoomed into the short circuit SFRA test and I'm concerned because they're not within that range, that 0.1 dB limit. You could always go over to interwind. It's considered an optional test, but if you did a capacitive interwinding measurement, you could check at the 60 hertz and see, or 50 hertz, and see, you know, how those three phases are behaving. It would mimic basically doing a CHL test on a three-phase transformer. However, you're now doing a CHL test on A phase, B phase, and C phase, which is kind of nice. So that's a very, that would give you a very sharp look to see if you had, so for some winding deformations. So for some of these tests, my point would be for any of the tests other than the open circuit SFRA tests, we can apply some types of limits, but as Volney had shared before, it gets a little bit more challenging when you are looking at the open circuit traces. It depends a lot on, hey, what frequency bandwidth am I in, and because certain areas, even frequency-wise, you may be concerned about a different correlation than at others. So there are software algorithms that provide some assist with all of that, like Volney had described.
All right, cool. The next question is going to be for Sanket. Does temperature have any outcome on the tests? What is recommended for testing as far as LTC and NLTC positions?
Okay, so good question. Temperature, I didn't mention it in the presentation, but it's always a good practice to note the temperature on the test report, and that's because temperature may result in negligible differences. It doesn't have a major influence on the measurements, but if the temperature difference is going to be large enough, then you may see some amount of deviation in your response. Again, it's typically going to be negligible. It's not going to be a lot. So it's always a good practice to note the temperature in your test report. As far as testing on LTC and no load tap changer positions, I did mention it in the presentation that I did mention my presentation what the recommendations of the IEEE are, and what they say is do it on the extreme raise tap on a winding with LTC, and that's because in the extreme raise tap the whole winding is in the picture. And if you're operating on if you're testing on a winding with a DETC, just do it on the in-service tap. DETC is and the name for no load tap changer. This is what the IEEE recommends. Different practices are followed all over the world. I believe in the IEC it says that it needs to be done on the extreme taps and the nominal tap. It's up to you. The IEEE makes recommendations, but you want to at least make sure that you have the in-service tap position measurements, because this is all about site reference, right? So you want to make sure that you get your reference test results. You have your reference test results in place. So if your transformer is going to be operating at a certain tap and you know that tap position is not going to change over the years much, then you want to make sure that you have the reference test results for those tap positions.
All right, next question is also going to be for you, Sanket. You said that manufacturers perform tests on new transformers. How long have they been doing that? Recently, we've been installing transformers that have been sitting around for 10 or more years. We're wondering if we would have a test to compare that to.
So SFRA test is a newer test compared to the other tests. When I say newer, I say comparatively newer. SFRA has been around for a while. I would say close to 20 years. So it's been around for a while, but it only started to be. It's always been a special test. So it's not been a routine test. So it kind of varies from manufacturer to manufacturer. Special test is a test which is done by the manufacturer when a customer asks for it, the customer is willing to pay for it. Some manufacturers have a practice of doing this test internally, regardless of whether the customer asks for it or not. So they have the records in place. So if you could certainly contact the manufacturers and find out if they have those records with them. And again, it depends on. It varies from manufacturer to manufacturer. It's a special test as far as I know. I don't know if it has changed now, but it's been a special test for at least 10 years ago. I'm pretty sure it was a special test. Yeah, it really depends on what the manufacturer did back then.
All right, it looks like we have time for one more question, and that's going to be for Volney. Can SFRA be done on other equipment like motors and generators?
So related to an earlier question, and the answer is yes. I know that there's some research on applying SFRA to motors and generators. There are some good papers on that on IEEE Explore, and the challenge there is, of course, the mechanical part. The test depends on the mechanical condition, and if the test is done with the rotor inserted, then the test will depend on the position of the rotor. However, also I don't think there's any standard yet, and the analysis will be a little bit different, or you will need to consider more things there. than for regular transformers. So it's more developed for transformers, but there's also developments or research on motors and generators. So I encourage people, if somebody's interested in that, going to IEEE and looking for some references there.
All right. It looks like that's all the time we have for questions. We apologize if we didn't get your questions today, but we will follow up with you in the next couple of weeks. Thank you all for attending. If you could please remember to answer the survey. The survey will also include a field for you to request a quote or a demo if you're interested. But thank you all again once more for attending, and have a great weekend.